In this video, I'm going to cover the last type of empirical formula problem. This is going to be one of the most challenging types because it does involve the most work, but I want to definitely show you some of the important aspects of calculating an empirical formula. So just kind of run through this real quick. Remember, the empirical formula is the smallest whole number ratio. And again, if you want to read through this again, it talks about you can only find it by experimentation, and you can indicate the actual numbers of present. And we're actually going to, at the very end or in the middle of this video, get into how to calculate a molecular formula as well. Again, these are the three ways you can calculate the empirical formula. You should have already done percent composition. You should have already done lab data. And then the one we're going to hit today is we're going to talk about combustion. But here is the important part right here. Determine the mass of carbon in CO2, determine the mass of hydrogen and water, and you have to get the mass of oxygen through subtraction. And this is why this is the most challenging part, and we're going to work one of these problems just so you can see how it works, okay? So we're going to kind of skip through all of these because hopefully you can understand exactly how to work this. So here's the first slide. So compounds containing carbon, hydrogen, and oxygen are routinely analyzed through combustion in chambers like this above. So if you notice, what you have is you have oxygen. Now let me ask you something, and when I've mentioned this before, why do you have to have oxygen in combustion reactions? Again, when I think of combustion, I think of boom, and when you think of boom, you think of fire. And well, the only way to have fire is you have to have oxygen. So what they're going to do is they're going to pump oxygen into a furnace. Well, what is a furnace? So something gets really, really hot, and then you're going to have a sample containing carbon, hydrogen, and oxygen, and then you have basically a catalyst right here. Copper oxide is just going to make this reaction go a little bit faster. You've got the water absorber, and then you've got the carbon dioxide absorber. So what it's going to tell you is it's going to tell you the concentration. We're going to talk about this a little bit later on in this session, and what I'm referring to as the concentration is a term called molarity. And again, it's just telling you how much water is in this sample and how much carbon dioxide is also in the sample when you burn it with oxygen. Okay, but again, the key is, and it's very important that you understand this, that carbon must be determined from the mass of CO2. Well, why is carbon going to come from CO2? Because if you remember, anytime we have a hydrocarbon combustion, which is cxhy, where x and y can be any variables, burned with oxygen, which is O2, you're going to get two different types you're going to get two products. You're going to get carbon dioxide and you're going to get water. Always, every time you have a hydrocarbon combustion, which is again cxhy, where x and y are any variable. And so the carbon has to come from carbon dioxide. Well, that should make sense because the only product where you have carbon is the carbon dioxide. And then it says the amount of H is determined from the mass of water that is produced. Well, why does it have to be water? Well, water is the only compound that has hydrogen. Well, then it's the weird part, and it's the most difficult part. It says oxygen is determined by the difference after the C and H have been determined. Well, the reason that makes it a little bit more complicated is because if you notice, oxygen is in the presence of carbon dioxide and water, which is going to make it a little bit more challenging for us to be able to determine the oxygen content in both of them. And so it has to be done by a difference, which we know in all math terms is going to be a subtraction. Okay, so let's look at a problem. It says the combustion of 5.23 grams of phenol yields 14.67 grams of carbon dioxide, 3.01 grams of water, and then phenol contains only carbon, hydrogen, and oxygen. And then it says, what is the EF? And we know that the EF stands for the empirical formula. Okay, so the first thing we got to do is, like the note just said, we've got to find how much carbon is in this 14.67 grams of carbon dioxide. So now, this is going to be a little different from what we've done in the past, and this is why I told you this is kind of the most challenging type of empirical formula problem. So it said that we had 14.67 grams of CO2. Well, here's the deal. I'm going to kind of run through this really quickly, but I want it to make sense to you. And so here's the problem. We've got to get this carbon out of this CO2. Well, if I'm starting with grams of CO2, I know I've got to change. I've got to get grams of CO2 on the bottom. Okay? Well, I know this. If I have grams of CO2, I know that that has to come from the periodic table. Well, I've got 44.01 grams of carbon dioxide, and that is going to be the mass of carbon dioxide always. That may be a number you want to commit to memory because you will use it quite often. And then here's the tricky part. I'm actually kind of cutting some corners just because it can make sense. If you will apply this knowledge, this will make things go a lot smoother. And I know I've told you to never, ever, ever, ever do this, but it does cut down on your work, and it makes everything run a lot smoother. I know I've got to get to how much carbon is in this carbon dioxide. So this is the one and only time that I'm going to go from grams of something to grams of something. Now, you could actually run the mole to mole ratio and the atom to molecule ratio and all that kind of stuff, and everything's going to work out, but I just want to show you this. So here's the deal. Of this 44.01 grams of CO2, how much of that was carbon? Well, this should make logical sense. Well, I know the total mass, and then I know that I need this one carbon. Well, that one carbon weighs how much? Well, if you look at the periodic table, it is 12.01 grams. Okay? So of the 44.01, 12.01 of that is carbon. And so that gives me, once I run those numbers, it is going to give me exactly 4.00 grams of carbon. Okay, so that takes care of my carbon content. And then it tells me I have 3.01 grams of water. Now, what am I getting out of the water? I've got to get the hydrogen out of the water, okay? And so just like we did a second ago, so if I have grams of water on bottom, again, this is one of the only times I'm going to go gram to gram. All right, but this time I need grams of hydrogen and hydrogen only. Guys, this is where everybody makes a mistake. It is not H2. It is just hydrogen that we're worried about. Again, this is not the hydrogen molecule that we're worried about. We are just worried about hydrogen. Now, hopefully you know that the mass of water is 18.02. And of that 18.02, how much of it was hydrogen? Well, now in the water part, there are 2 hydrogens. But remember, every hydrogen is 1, but you've got 2 of them. So if I took the total and I subtracted it from how much hydrogen was present, there would be 2.02 grams of hydrogen remaining. And the way you could have done that very simply was you could have said, okay, well, if I have 18.02 grams, and I know that some of it is H, and some of it is oxygen. Again, this is total right here. Well, if I know the amount of oxygen, well, oxygen is 16. Well, that leaves me with 2.02 grams of hydrogen left, okay? All right, so when I run these numbers, that is going to give me 0.337 grams of hydrogen. Okay, well, now I know my mass of hydrogen and I know my mass of carbon. And this is the difficult part. Remember when we talked about, a long, long time ago, this idea of the conservation of mass? And all this is simply meaning is what you start with is what you end with. So the amount of carbon you have in the beginning must equal the amount of carbon you have in the end. The amount of hydrogen you have in the beginning is the amount you have in the end. The amount of oxygen you have in the beginning is the amount of oxygen you have in the end. And so you've got to learn how to be able to keep this conservation of mass afloat. Well, it told me up here that I started with 5.23 grams of phenol, and phenol only contains carbon, hydrogen, and it also says oxygen. Well, think about that for just a second. If I know how much carbon and hydrogen I have in the end, shouldn't I be able to determine how much I had in the beginning? I know how much I started with. And so here's the deal. I know that I total started with 5.23 grams of carbon, hydrogen, and oxygen. Well, in the end, I know my carbon content was 4.00 grams, and I know that my hydrogen content was 0.337 grams. Well, the only thing that I'm missing is oxygen. So if you go back, it told you have to find the oxygen content from the amount of the products remaining after you found the amount of carbon and amount of hydrogen. So this should make sense. So if I know how much hydrogen and carbon I have left, I can subtract it from the initial amount because the law of conservation mass states of what I have in the beginning, I should have in the end. This should tell me exactly how much oxygen I should have present. And so when you run these numbers, you should get a total of 0.893 grams of oxygen. And so now I know exactly how much oxygen I had in the beginning and how much I had in the end. Okay, so now from this point, everything is going to be the exact same. And like I said, this is the most difficult part of an empirical formula problem because it's the longest and the most drawn out. But once you get to this point, everything is the same that you've done from this previously. So if you look at it now, you have 0.893 grams of oxygen. Well, if you completely ignore everything we've done and we just start from this point forward, you should recognize a common theme of everything that you've done. Well, I've got grams. Well, every time you had grams in empirical formula, what was your next step? Hopefully you said, if you have grams, you got to convert them to moles. Well, that's exactly right. So we've got to go from grams of carbon to moles of carbon. We've got to go from grams of hydrogen to moles of hydrogen. And then I've got to go from grams of oxygen to moles of oxygen. And this is exactly what we've done in the previous steps. All right, so I know that there are 16.0 grams of oxygen in 1 mole. There's 1.01 grams of hydrogen in 1 mole. And there are 12.01 grams in 1 mole of carbon. All right, and so when I run these numbers, it's just like last time. I know I'm going to get my number of moles of each one. And so I have 0.333 moles of carbon, 0.334 moles of hydrogen, and I've got 0.0558 moles of oxygen. All right, well, I know what you're going to ask next. Okay, well, I've got moles. What is your next step in solving for the empirical formula? So your first step is convert grams to moles. Your second step is divide by the least number of moles. Well, oxygen should be the obvious choice here. 0.0558, 0.0558, and 0.0558. All right, well, this is the last step, and this is the one that's crucial because you've got to make sure that you adhere to. I have the 1-9 rule in terms of in the notes, but I think I may transition and start calling it the 3-8 rule, which means if you have a 3 or an 8, it's wrong. Okay, so if you have a 3 through 8, you're going to have to multiply these values. Anything other than that, you're good. Round to just make sure it's an even number. Okay, so in this case, when I actually multiply these numbers out, you're actually going to get some good answers here because the final answer for the carbon when you divide is going to come out to be 6. The final answer for hydrogen is going to come out to be a whole number of 6. And then the last one, of course, obviously divided by itself, so it's going to be 1. And so these are your numbers that you're going to plug into your empirical formula. So it is C6H6O. And this is your final answer for the empirical formula. Again, I know it is a lot. It is the most challenging type of problem in terms of empirical formulas when it's with combustion. But the key is this part right here. We're making sure that you know that you have to adhere to the conservation of mass, where you got to start out by finding the mass of carbon from carbon dioxide, finding the mass of hydrogen from water, and then subtracting those two numbers from the total mass that was given way up here in the top, and that will determine your amount of oxygen content. And then everything from there on out, which is in the yellow box, I know it's difficult to see, but everything in this box is normal from everything else that you have to do. Okay, and again, the last little tip and the last little trick that I just want to reiterate one more time is make sure whenever you do convert from carbon dioxide to carbon that you can go from 44 grams of carbon dioxide to 12.01 grams of carbon, and this is the big one. Everybody always messes this one up. In 18.02 grams of water, there are 2.02 grams of just hydrogen. Okay? All right, so hopefully that will make sense. Okay, the next thing that we're going to talk about, and this is just as easy basically because it's the empirical formula versus the molecular formula. The key here is the definition of the molecular formula is it is the actual number of atoms in the compound. because when we're doing the empirical, we're solving for the simplest ratio. Everything has basically been reduced. But in the molecular, it is the exact number of atoms present. So whenever we talk about H2O, this thing cannot be reduced anymore. But when we talk about hydrogen peroxide, it has the ability to be H2O2. Well, if you understand how math works, do you know that this can be reduced to HO? But as I've said, there is no such thing as a HO in chemistry. So you have to be able to deduce that this is the molecular formula and this is the empirical formula. Okay? Just like glucose, C6H12O6. We know glucose is this formula. Well, is this the molecular or is this the empirical? Well, it has to be the molecular because it is the exact number and it can be reduced to CH2O. Well, we don't ever deal with anything called like that, okay? So we've got to determine, once we know our empirical, how do we convert it to our molecular? And so I've kind of given some steps in order to be able to figure out how you do it. So number one, to determine the molecular formula of a compound, you must know the formula mass of the compound. And the great news is that it must be given in the problem. If it's not given, you can't do it. Number two, once you have solved, now keyword there, notice what it says, you have solved. You're going to have to put forth a little bit of effort to solve for the empirical formula. Okay, then you're going to need the molar mass of the empirical formula. You have to calculate this. If you don't calculate it, you're not going to be able to do the problem. So number one, the given in the problem is the molecular formula's mass. Okay, and then you have to solve for the empirical formula mass. Once you have both, the mass of the MF, which is the molecular formula, again, it will be given to you, and the mass of the empirical that you have to solve for, you're going to plug these numbers into the following equation. So it is the molar mass of the MF over the molar mass of the EF. And again, another easier, simpler way to say it is just the number that they gave you divided by the number that is solved. This should be a whole number. Okay? And once you have that number, you're going to take it and you're going to multiply it times the subscripts in the empirical formula. So if you notice, it was AX, BY. And X and Y can be any numbers. And so what we have is we're going to multiply each subscript by that total. And then it's just going to give you the brand new subscripts, which is going to equal the molecular formula. Now, one thing I do want to point out, sometimes the molecular and the empirical are the same thing. The molecular and the empirical can be the same thing. Okay? So don't worry is if sometimes you get Z, which is a whole number, and it comes out to be 1. That is possible. Okay? So don't worry if you actually come up with those kind of numbers. It is possible. So we're going to work through 3 of these problems real quick. All right? One other point of emphasis to kind of point out, the formulas for ionic compounds are empirical, and the reason why that ionic compounds are empirical, and again remember empirical means reduced, is because ionic compounds have charges. So if you think about it, if we do zinc, which is 2+, and we do oxygen, which is 2-, have you ever written Zn2O2? Well, if you have, you've done it wrong. You know that it is always going to be reduced to ZNO. However, a molecular formula, again, and remember, molecular formula comes from a covalent bond. The whole number multiple of an empirical formula is what a molecular formula is. And so, again, we're going to be able to do these things. All right, so problem number 1. Determine the empirical and molecular formula for a compound that gives the following analysis in mass percent. So again, when you see a percent, it should be very simple. You should know the rule is drop the percent and change it to a gram, right? Now, let me go ahead and forewarn you that these compounds are out of order. Normally, you write them in the order that they are given, but for some reason, these got out of order. So we're going to do carbon first, hydrogen second, and chlorine third, okay? So let me zoom in, and we're going to go ahead and get started on this problem. And so it tells you that you have a total of 24.27. Try that again. 24.27, and again it says percent, but we're just going to drop it, change it to grams. Of carbon. It tells you that you've got 4.07 grams of hydrogen, and then finally you've got 71.65 grams of chlorine. All right, so the first thing we've got to do is convert grams to moles. Remember, in all empirical formula problems, that's the first thing you do. And again, sometimes we get lucky and they give us problems already in moles, so it makes it a lot simpler. Grams of Cl to mole of Cl. All right, anytime you have mole and gram together, mole gets a 1. And then the grams are going to come right from the periodic table. So carbon is 12.01, hydrogen is 1.01, and chlorine is 35.45. Okay, all right, so when you run these numbers, you're going to get 2.02 moles of carbon. You're going to get 4.03 moles of hydrogen, and you're going to get 2.02 moles of chlorine. Well, the good news is that your third step, again, step number 1 is convert grams to moles. Step number 2 is, let me back up. Step number 1 was drop percent, change it to gram. Step 2 is convert grams to moles. And step 3 is now divide by the smallest number of moles. Well, 2 of them are the same, and so we're going to divide them by the smallest number, which is 2.02, 2.02, and 2.02. And so it should be obvious to you what this should come out to be, which is 1, 2, and 1. And so our empirical formula, again, which is our most reduced version, is cH2Cl. And if you recognize, we know that this cannot be reduced in any shape, form, or fashion, okay? And so this is going to be our empirical formula. Now, remember it said also calculate your molecular formula as well. And so I just want to go ahead and show you this. Remember, the molecular formula is the mass of the MF divided by the mass of the EF. And remember, I gave you a simpler way to look at it. It's the number given divided by the number solved. Now, what am I going to be solving for? I need the mass of this thing. And so if you calculate 12.01 times 2.02 plus 35.45, you should have come out with a total mass of 49.48 grams per mole. And so that is going to be my number that is going to go in the denominator. So 49.48. And then the number given. Let's go back up to the problem. Let's look at it. And so the molar mass is known to be, and look what they gave you. It says molar mass known to be this right here. And so this is the mass of the MF. Okay, so now what we got to do is we got to go back down here and we got to plug this number in to our formula. So it's going to be 98.96. And so when I divide those numbers, I'm going to get a whole value number of 2. Okay, and so the way you can think about this is that I need to take these numbers, I need to take the empirical formula, which is cH2Cl, and I need to distribute that 2 to the entire thing. And so my empirical formula is going to turn into C2H4Cl2. And that is my final answer. That is my molecular formula as well. Okay? All right, so let's move over to the next problem. All right, a white powder is analyzed and found to contain 43.64% phosphorus and 56.3% oxygen by mass. The compound has a molar mass of 283.88 grams per mole. What is the compound's empirical and molecular formulas? Okay, so let's just work it the exact same way. We'll zoom in right here. Okay, it tells us that we have 43.64 grams of phosphorus, and we have 56.36 grams of oxygen. Okay, and so again, step number 1. Again, it was given in percents, but we know we can just drop the percent and change it to gram. And so after that, I know that I need to go from grams to moles, and I need to just plug my numbers in. And so in 1 mole of phosphorus, there is 30.97 grams, and in 1 mole of oxygen, there is 16 grams. And so when I run those numbers, that is going to give me a total of 1.41 moles of phosphorus, and this is going to give me 3.52 moles of oxygen. Okay, all right, so then I know my next step is to divide by the smallest, which is going to be phosphorus, which is, let me change that color so you can see it, which is 1.41 divided by 1.41. And something interesting is going to actually happen in this problem. When you do this math, you're going to come up with 1 and you're going to come up with 2.5. And this is where we have that 3/8 rule. If the first number to the right of the decimal, which is this 5, is a 3 through an 8, something is wrong. So what you need to do is you need to multiply both values by 2. Both values, not just the one that's off, both of them. That's the important key aspect here, okay? So when you do that, it should be obvious what's going to happen. You're going to get a value of 2, and you're going to get a value of 5. Well, now that's going to give us our empirical formula, which will be P2O5. And again, this is our empirical formula right here. Now, let me just go back and talk about a point right here. Let's pretend that for some reason this number did not work out to be a whole number. Let's just say it came out to be 5.7. Well, that's the 3 through an 8, so that's not going to work for us. What we have to then do is go back to the original number again. And again, it's the original number. And multiply both of them by 3 and by 3. Okay, and if that doesn't work, then come back and multiply both of them by 4. So you have to continue. Guys, and I've never seen a problem to go over 5. If you get to 5, something is wrong, go back and check your work. Okay, and so now we need to do the molecular formula. Again, it's the mass of the MF, which is given, over the mass of the EF, which is solved. And I need to go back and I need to solve that. The mass that is given in the problem is 283.88, and then the calculation of the mass of the empirical formula turned out to be 141.94 grams per mole, which is what I need to plug in for solved. So 141.94, and so this should be obvious. It gives you a number of 2. And so what I need to do is I need to multiply P2O5 by 2, which gives me P4O10. And this is my molecular formula. All right, so again, I've kind of worked this one out for you to kind of hope. So it tells you nitrogen ammonia gas reacts with oxygen gas. Remember, oxygen is a diatomic. It's going to yield nitrous oxide, and it's going to yield water vapor. I've actually kind of balanced this one. This one did not record as I was teaching through this, and so if you just kind of stare at it for just a second, hopefully it will make sense to you, and you'll understand it. So again, I needed 1 N and 1 N. I had 3 hydrogens and 2 hydrogens, so I had to make them 6 from this 2-3-6 rule, and then that gave me 3 oxygens and 1 oxygen, which gave me 4, and so that's where the 2 came from. And so the last part about balancing equations, again, is number 1, you must know all 7 diatomics. Remember, it's all the gens, so it's hydrogen, nitrogen, oxygen. Matter of fact, let's make this right. If we're going to do it, let's do it the right way. Let's make them diatomics. So I've got H2, I've got N2, I've got O2, and so hydrogen, nitrogen, oxygen, and the halogens, which is F2, Cl2, Br2, and I2. Number 2, make sure all formulas are correct. Okay, balance the left and the right side, and the coefficient should determine the mole ratios. Okay, so again, those are the important aspects of this particular slide. Again, this whole entire chapter is about stoichiometry, and we've been doing a lot of that, but I just cannot stress how important this thing is in terms of just knowing how to convert from one thing to the other, knowing what a mole-to-mole ratio is, or knowing how to go grams to moles, because when I say this, I mean it. It never, ever, ever goes away. Okay? Again, you've got to understand how to do this concept. So, again, this is a little mole map if you want to kind of pause the video there and look at it. This is the one that I think is going to be the most important that we'll get to later on whenever we go through gases. And it's knowing at STP, we have 22.4 liters in 1 mole. I know you do not have this in your video or in your note packet, but again, it is something that we'll talk about a little bit later. Okay, first you have to be proficient with the following no matter which method you choose. You have to write the correct formula. Bottom line, you've got to know how to do the formulas. Number 2, you've got to calculate correct molar masses. Guys, this is very important. If you have the wrong molar mass, it's going to be wrong. And you get molar masses from the periodic table. And again, I stress, I know I do the molar masses for you a lot, but that's only because that's time-saving techniques that I wanted to be able to get through a lot more material, because I expect you to know how to solve molar masses. The third thing is a balanced equation, and then next you'll be able to know how to calculate the moles or anything else that you need, okay? All right, there are only 2 rules for stoichiometry in a basic sense. Number 1, you must have your given in moles, because to go from one thing to something else, you are going to have to get it to moles, because that's the only way to do it. And you can only move from moles of one substance to moles of another by using the mole to mole ratio. Okay, that's very important. And remember that no matter how complex it may seem, you can only go one step at a time. And so you know what you're starting with, you know where you're going. There has to be a relationship, there has to be some type of ratio in order to get from one thing to the next. And the last slide for this video, I want to cover one very small problem, and it's very simple. And notice the very first thing is we've got to balance this. Okay, so if you notice, I've got 1 Na, I've got 1 Na. I've got 2 hydrogens, I've got 2 hydrogens, and then I've got 1 H. Excuse me, let me retract that. Let me start back over, because I knew I messed it up. I've got 1 Na, 2 H's, and then I've got 3 H's, okay? Well, that's going to be a problem for me, because I know I need to balance up those H's. The way to make this the easiest is let's go ahead and make it 4 on the right side, but don't double the 2. The H2, let's just put a 2 right here. Well, that gives me a total of 4 H's on the right. Well, now if I put a 2 right here, that gives me 2 hydrogens, that gives me 2 oxygens, and now I just need to put a 2 in front of the sodium. So if that kind of threw you off, maybe pause the video, rewind it, and look at it one more time. We haven't really got into this, but at the very next slide, the first slide of the next video is going to get into excess versus limiting reactants. Guys, this right here, you should jump for joy. If they say excess, that is a great thing. That automatically tells you that sodium is our limiting reactant, okay? So number 1, it says balance. It says convert grams of Na to moles of Na. Well, I hope that you know that you recognize you're going from grams of Na to grams of hydrogen. So guys, this is just a 3-step gram to gram equation that should not get any more complicated than anything you've ever done. So I'm starting with 12.5 grams of Na. Well, I know that I need to get rid of grams of Na. So the first thing I'm going to do is I'm going to put it on the bottom to cancel it. Well, I've got to get from sodium to hydrogen gas somehow. Well, if you go 2 slides back, it says the first thing you've got to do is you have to get this thing into moles first. Because without moles, you're not going to be able to do any converting. So I know that I need to go from grams of sodium to moles of sodium. Okay? All right, well, now I know that that is going to cancel my grams and my grams. Well, let's move on, because I can't stop there. Well, I know that I need to cancel moles of Na, so I'm just going to put it on the bottom. So I'm at moles of Na. And what do I need to go to next? I know there's got to be something on top, and I know that eventually I've got to get to H2. Well, this is your major step right here. So this is my mole-to-mole step. This right here is my mole-to-mole ratio, and again, it's going to come from your coefficients, okay? And so this is the most crucial step right here. So let me change that. I don't like the color scheme there. So I've got to get to moles of H2. Well, I know that in good news. I know that my moles of Na have canceled, leaving me with moles of H2, but I cannot stop. I got to go one more because it asked me specifically about grams. So when I have moles of H2, I can now go to grams of H2. All right, so if anytime I ever see mole and gram together, that's simple. Mole should get a 1. Anytime I see grams, I get it off the periodic table. The great news is that these will come right off the periodic table. So sodium is 22.99, H2 is 2.02, and then finally the big one, the mole-to-mole ratio. Hopefully you know that this will come from the coefficients of the problem. And so top to bottom, my mole-to-mole ratio is a 1 to 2. And again, if you're still kind of confused, like, okay, I don't know where that came from. The mole-to-mole ratio, again, this is going to come from right here. Okay, it's going to come from that coefficient, and this is going to come from right here. Okay, so that's where those numbers come from. And when you run the numbers on this, when you run the calculation, you should come up with a final answer. And again, I want to make sure that you understand this, what you start with. Remember, I know we don't talk about this a whole lot, but make sure your significant figures are maintained. There are 3 sig figs in that particular problem, and so over here we've got to make sure we maintain 3 sig figs, and the final answer comes out to be 0.549 grams of H2, and that is it.